object falling through fluid this way. So the force of gravity is acting down on it, and the fluid is going to have some sort of a drag force acting on it. They give us other miscellaneous information. The mass is 12 grams. They discuss other such things, which we'll get back to later. Then this is the data that the students collected. So obviously there's a curve downward, so we assume that eventually this curve will get flat, at which time we would get to terminal velocity, right? So A1 is a reasonably simple question. It just says, does the speed of the object increase, decrease, or remain the same? Well, as time goes by, the velocity is going up, so this would be increase. Now, question 2. In a brief statement, describe the direction of the object's acceleration and how the magnitude of this acceleration changes as the object falls. So, the magnitude or the direction of the object, simple enough, the direction of it is downwards because it's going down, right, according to the picture. It's moving downwards, and even though this is an absolute value function, it's getting faster and faster and faster and faster in, it's getting faster and faster and faster in the negative direction. So the acceleration is negative or downward, depending on how you want to write it. Both would be acceptable according to the key. Now, what happens to the magnitude of the acceleration? Well, if we remember that the acceleration on a velocity versus time graph is the slope, well, in the beginning, it's relatively steep, less steep, less steep. So it's getting less and less steep as it goes. So the acceleration, the magnitude of the acceleration, the value of the acceleration is decreasing. So we have decreasing magnitude. And we already discussed that eventually it's going to get to some sort of a terminal velocity, at which point it would go to 0. So it's going down and down and down and down until eventually it gets to a point of 0. Okay. Now, A3 says, using the graph, calculate an approximate value of the magnitude of the acceleration at a time of 0.2. So we're going to go back to the picture. We're going to clean this up a little bit. Okay. And it says at 0.2. So here's 0.2. So we're going to make a line at 0.2. Okay. Now, if we're looking at this particular line, I'm going to try to find some points that kind of go through a nice XY location. So we could choose maybe that one. And let's say that one. Okay, so we're going from 0.6 to here, which would be 0.82. So we're going from 0.6 to 0.82. So 0.82 minus 0.6. And then we're going from 0.14 seconds to 0.25. Okay, so we have 0.82 minus 0.60. That's going to be 0.22 divided by 0.11, which nicely enough turns out to be roughly 2 meters per second squared. Now, the key said 2.2 meters per second squared, and there's definitely going to be some room for error here. Obviously, my line is kind of thick, so maybe it didn't come out exactly the way I did. Maybe I just tried to fudge it a little bit. So let's just say it's got to be somewhere in the 2 to 2.4 or so range. Okay. Now, this is a familiar looking formula because we've done a couple of these now. Students use the equation V equals A and then 1 minus e to the negative bt to model the speed of the falling object, where A, they give you a value for it. So they give you a value for A, and they give you a value for B. So it says, Use the above equation to derive an expression for the magnitude of the vertical displacement of the falling object as a function of time. So they gave us a function for v, and they want y, or they want displacement, okay? So what we're going to have to do is we're going to have to take that v, which is a minus ae to the negative bt. I just distributed the a. And we're going to have to find the integral of it. Okay, so we're going to say integral of, so y is going to be equal to the integral of, say from 0 to t, some random t, of a minus ae to the negative bt dt. Now, this kind of gives us a little bit of the shivers here for a second, but don't panic. Not as bad as you think. So the integral is going to be integral of a dt is just at. Now, the nice thing is on your reference table, they give you the integral of e a to the x. And that's just 1 over a e to the ax. Okay, so we're going to take advantage of that, and we're going to say that this, so we have the a, that's a constant, and then we're going to have 1 over negative b, because that's taking the place of the a here, e to the negative bt, and then we're just going to evaluate this from 0 to t. Okay, so let me add another page here so we have more room. So we're going to say that it's going to be at minus, no, let's go back for a second. Because we have the minus here and the minus here, this is going to end up being plus. So plus a over b e to the negative bt minus, well, a 0 plus a over b e to the negative b times 0. So this whole piece ends up becoming one. So our final answer for this is going to be just AT plus A over B minus 1. Okay. Now, if we want to plug in the numbers now, that's going to be 1.18 t plus 1.18 over 5 e to negative 5t minus 1. Okay. Now, the answer key took it a step further. The answer key factored out the 1.18, and then we just have t plus 1 over 5 e to negative 5t minus 1. So that's what the answer key actually told us. Okay. Now the next one says derive an expression for the magnitude of the net force F of t exerted on the object as it falls through the fluid as a function of time. Okay. So this one, again, looks like it's going to be kind of a pain in the butt. So what we have to work off of is F equals ma. Okay? they gave us m. Check. So if we're looking for f of t, we have to look at this as a of t. So if we have a velocity, which they gave us in the beginning, the velocity was, hold on a second, a 1 minus e to the negative bt. And we have to do the derivative. We have to do the derivative of this, dv dt, to get a. So we're going to say d dt of a 1 minus e to the negative bt. Okay. So I'm going to distribute this, right? I'm going to say a minus ae to the negative bt. Okay. Once I have this, and I want to do the derivative of this, well, the derivative of a is just going to be, it's going to go away, right? So now I'm left with negative a e to the negative bt. Now, on your reference table, again, coming to the rescue, they tell you that d dx, so the derivative with respect to x of e a to the x, is just a e to the ax. So if we use that here, we're going to say negative a times negative b, right, that's what this is, e to the negative b t. So negative a times negative b gives me positive ab e to the negative bt. So that would be an expression for the acceleration. Now, remembering back to having to do f equals ma, we have f equals m, forgive my memory, a b e to the negative bt. And now if we put our numbers in here, you have to go all the way back to the very beginning. The mass was 12 grams, so that's 0.012 kilograms. A is the 1.18. B is 5. E to the negative 5t. And I'll spare you having to pull out your calculators. That ends up being 0.071 e to the negative 5t. Ta-da. Now, C1 says a student repeats the experiment with a taller glass cylinder that is filled with the same fluid. The cylinder is tall enough so that the object reaches a constant speed. So this is that terminal velocity we were talking about before. Determine the constant speed of the object. Well, there are different ways of doing this. The easiest way to do this would be, let's talk about, we'll take v of t, which was the original a, I'm just distributing, negative bt. Now, if I let t go to infinity, that will guarantee that we've reached terminal velocity. So, if I do that, if I let t here go way, 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 way up, this term gets very, 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 very close to 0, which makes life easy, because then my v of t, or my v, let's write it, my v terminal, when this goes to 0, is just a. All right, so v terminal would be 1.18 meters per second. So it's a nice little trick. You know that at time equals infinity, it would have to be a terminal velocity because there's some point before infinity it gets there. And you know your basic limits. When that gets to infinity, this whole term becomes 0. Okay, 2. Determine a force exerted by the fluid on the object at this time. Well, when the acceleration is 0, that means that the net force is 0, right? Net force is ma. A would be 0, and therefore this would be 0. Now, the net force is force of gravity, or let's do it this way. Guess we're going to stick with proper conventions here. Force drag minus force of friction equals 0. That just means the force drag has to be equal to the force of friction. Now, the force exerted by the fluid is the force drag. So that's what friction. Yikes, Michael. You did not mean friction here. I meant gravity. See, I mess up even in video form. So, force drag equals force of gravity. Now, force of gravity is 0.012 kilograms. And we're going to say 10 meters per second squared. So, times 10 meters per second squared. So, the force drag is going to be yikes. Really tiny screen, guys, sorry. 0.12 newtons. End